Hi friends, today we are going to explain Maxwell equation in scalar and vector potential. We know the general solutions to Maxwell equations are del dot E equal to rho by epsilon. This is called Gauss law. We all know that. Then del dot B equal to 0, no name for this. Del cross E is equal to minus dou B by dou T is Faraday's law. Del cross B is equal to mu naught by J, Ampere's law. These four are the general Maxwell's equation. For the above question, we have to write the Maxwell's equation in scalar and vector potential. For that, we have del dot equal to rho by epsilon Gauss law, del dot B is equal to 0, no name, del cross E equal to minus dou B by dou T Faraday's law, del cross B equal to mu naught J plus mu naught epsilon dou E by dou T Ampere's law for scalar and vector potential. In electrostatics, del cross E is allowed us to write E as the gradient of scalar potential. We know that in electrostatics, del cross E equal to 0, which allowed to write E as a gradient of scalar potential. That is E equal to minus del V. In electrodynamics, this is no longer possible because the curl of E is non-zero. Here in electrodynamics, is not possible to write because the curl of E is non-zero, but B remains divergence. Their gradient del cross equal to 0 in electrostatics. That's why we can write E as gradient of scalar potential. In electrodynamics, this is no longer possible. The curl of E is non-zero, but B remains divergence-less. So we can write B equal to del cross A. B is equal to del cross A. This implies second equation. This is first equation. As in electromagnetics, putting this into Faraday's law 3, Faraday's law, which is this one, del cross equal to minus dou B by dou T. Here we know that B is equal to del cross B. So put that B value as del cross A. Then multiply the del into this equals to comes this side, that minus sign becomes positive, then dou A by dou T is equal to 0. Here is a quantity unlike E alone, whose curl does vanish. The curl does vanish. It can therefore be written as a gradient of scalar. For gradient of scalar, that's why we are writing that E plus del A by dou T is equal to minus this del dot V. In terms of V and A, in terms of E, we are writing V and A, we are taking that E is equal to minus del V. We have put this, that dou A by dou T terms goes to this side, that is minus dou A by dou T, which implies equation number 3. This reduces to the old form when A is constant. The potential representation automatically fulfills the two homogeneous Maxwell's equation, that equation 2 and equation 3. Then how about Gauss law equation 1 and Ampere's law equation 4? For equation 1, that is del dot E is equal to rho by epsilon naught. For del E, we got the value of minus del V minus dou A by dou T. So substitute that value in first equation, that is Gauss law, that del into minus del V minus dou A by dou T is equal to rho by epsilon naught. Multiply this del inside, del square V minus dou A by dou T into del dot A is equal to integral rho by epsilon naught, taking del square V minus dou by dou T of del dot A is equal to, that negative sign comes this side, dou rho by epsilon naught is called equation number 4. This replaces Poisson's equation. This is replaces the Poisson's equation, putting 2 and 3 in fourth, else putting that second one and fourth one equation in fourth, that is Ampere's law. We are putting that. That's now we are using a vector identity. First putting that del cross A is equal to mu naught J minus mu naught epsilon naught del dou v by dou t minus mu naught epsilon naught dou square a by dou t square. Here using the identity vector del cross a is equal to del, we know that del into del dot a minus del square into a, and rearranging this we get del square a minus epsilon mu naught epsilon naught into dou square a by dou t square minus, we are there taking only mu naught j to right hand side and all the terms in left hand side. This equation 4 and 5 contains information in Maxwell's equations.